Inorganic Chemistry, Chapter Metal Ligand Bonding, Crystal Field Theory. Crystal field theory is a model for the bonding interaction between transition metals and ligands. It describing the effect of attraction between the positive charge of metal cation and a negative charge on the non-bonding electron of the ligand. Crystal field theory was developed by H. Bith and V. Black in 1935. Assumptions of crystal field theory. Crystal field theory is an electrostatic model. It considers the metal ligand bond to be ionic. There is pure electrostatic interaction between the metal ion and the ligand. Ligands are treated as point charge and point dipoles. Point charge in case of ionic ligand, example F negative, Cl negative, Cn negative. Point dipoles in case of neutral ligands, example NH3H2O. If the ligand is neutral, the negative end of the dipole is directed towards the central metal cation. The 5d orbitals in an isolated gaseous metal atom have same energy. Same energy means they are degenerate. The 5d orbital still remains degenerate even when a spherical symmetrical field of negative charges surrounded the metal atom, a anion. When negative field of ligands become asymmetrical, means asymmetrical field of ligands surrounded the metal, then the d orbitals will no longer remain degenerate. As result, splitting of the d orbitals happens. Limitations of crystal field theory. Crystal field theory. This theory explains successfully the structures of complexes, magnetic properties, colors, and electronic spectra of the complexes. Crystal field theory considers only the metal d orbitals and ignored the metal of s and p orbitals. This theory has not considered the covalent character in transition metal complexes. CFT has also not considered the pi bonding in complexes. It cannot explain the relative strength of ligands as given in spectrochemical series. The compounds like CrCO6, NiCO4, in which metal is in zero oxidation state and the ligand is neutral, have no electrostatic interaction between the metal and the ligands not taken. Crystal field splitting in octahedral complexes. In a free metal cation, all the 5d orbitals are degenerate. In an octahedral complex, say Ml6 and positive, the metal cation is placed at the center of the octahedron and the 6 ligands are at the 6 corners. These 6 corners are directed along the Cartesian coordinates along x, y, and z axis. This is the structure of octahedral Ml6 and positive ion. When all the 6 ligands are at infinite distance from the metal cation, the 5d orbitals of metal cation not affected by ligand electrostatic field, so it will remain degenerate. But when the ligand move towards the metal cation, there are two electrostatic forces. One is electrostatic attraction and another is electrostatic repulsion. Greater the force of attraction between the metal cation and the ligands. Ligands will be more closer to the metal ion and hence more will be repulsion between metal d electrons and the lone pair of electrons. The force of repulsion between metal d electrons and the ligand electrons goes to increase in potential energy of the metal d electron. Greater the force is directly proportional to potential energy of attraction. If force is greater, then the potential energy will be greater. These are the structures of d orbitals: dx square minus y square, dz square, dxy, dzy, dzx. In dx square minus y square and dz square, in these lobes are on the axis. We can see in these pictures in dxy, dyz and dzx. In these lobes are in between the axes. We know that ligands are placed on axis and dx square minus y square, dz square orbitals are also placed along axis. So due to this, there is large repulsion between the electron in metal d orbitals and electron of ligands. Hence, due to more repulsion, energy of dx square minus y square and dz square will be more. And dx, dy, dz orbitals show lesser repulsion between metal d orbital electron and ligand's electron. Hence, due to lesser repulsion, energy will be less. The 5d orbitals which were degenerate in metal cation are now split into two sets of orbitals of different energies. A high energy level with two orbitals dx square minus y square and dz square have the same energy, and a lower level with three equal energies orbitals dxy, dyz and dzx. The set of dx square minus y square and dz square orbitals is referred as easy set, which is doubly degenerate, and the set of dxy, dyz and dzx orbitals is referred as T2G set, which is triply degenerate. In this diagram we can see dxy, dyz, dzx, dx square minus y square, dz square are 5 orbitals of degenerate d orbitals in free ion. This is average energy d orbitals in spherical crystal field. It splits into two forms, EZ and T2Z. In T2Z, dxy, dyz and dzx belongs, and in EZ, dx square minus y square, dz square exist. It is divided by barycenter crystal field splitting in octahedral field. Since the distance between the metal cation and the ligands has remained the same, the net potential energy of the system must remain the same as that of the spherical field before splitting. The separation of 5d orbitals of metal cation into two sets of different energies is called crystal field splitting. The energy difference between two sets of orbitals which arise from an octahedral field in terms of del naught, where del O in del O stands for octahedral. Therefore, since there are two easy orbitals, they must increase by 0.6 del O or 6 dq, and the 3 T2Z orbitals must decrease by 0.4 del O or 4 dq per electron. Crystal field splitting in tetrahedral complex. A regular tetrahedral geometry is obtained when a metal cation or atom is placed at the center of a cube and four ligands at alternate corners. In this diagram we can see. In this tetrahedral complex, the dxy, dyz, dzx orbitals of metal cation have large repulsion with electron of ligand than those of dx square minus dy square and dz square orbitals. Hence, due to large repulsion between metal cation and ligands, electrons having more energy degenerate d orbitals in free ion, d orbitals in spherical crystal field splitting in tetrahedral field. In this, d orbital is split into two parts, E and T2. In T2, dxy, dyz and dzx exist, and in E part, dx square minus y square and dz square exist. Crystal field splitting in tetrahedral complex. To maintain the rule of center of gravity, the dxy, dyz and dzx orbitals referred as T2 set are plus 0.4 del T above the barycenter, and the dx square minus y square and dz square orbitals referred as E set are 0.6 del T below the barycenter. The G subscript is not used with T2 and E sets because the tetrahedral complexes have no inversion center. The difference in energy of E and T2 sets is represented by del T, where T stands for tetrahedral. The crystal field splitting in tetrahedral is just reverse of the octahedral complexes. The crystal field splitting in tetrahedral complexes is smaller than that in octahedral complexes. Tetrahedral complexes are always high spin because del T is equal to 4 by 9 del O. Del T is much smaller than octahedral splitting del O. Del T is always less than the pairing energy due to no pairing of electrons occur in D3, D4, D5, D6, D7 tetrahedral complexes. Therefore, the tetrahedral complexes in configuration are always high spin whether the ligands are strong or weak. Crystal field stabilization energy CFSC. CFSC in octahedral complexes. In octahedral complex, the T2G set has energy of minus 0.4 dalom and EG has energy of plus 0.6 dalom related to barycenter. Minus and positive signs indicate decrease and increase in energy relative to the barycenter. The complex ion with one electron in one of the T2Z orbitals has energy of minus 0.4 del O. This indicates that in a complex ion of D1 configuration, 0.4 del O energy is released. This released energy is called the crystal field stabilization energy of the complex ion. The general electronic configuration for CFSE T2ZP GeZpQ and formula for CFSE. CFSE is equal to minus 0.4 P plus 0.6 Q into del O. Del T is equal to 4 by 9 del O. For D1 complex electronic configuration is T2Z1 and in EZ 0. CFSE is equal to minus 0.4 into 1 del O is equal to minus 0.4 del O. For D2 complex electric configuration is T2Z2 EZ0. CFSC is equal to minus 0.8 del O. For D3 complex electronic configuration is T32Z E0G. CFSC is equal to minus 1.2 del O. For D4 complex electronic configuration is T3 T2Z E1G. For high spin, CFSC is equal to minus 0.6 del O. For high spin complex electronic configuration is for low spin is T42G E0G. For low spin complex, CFSC is equal to minus 1.6 del O plus spin. When no pairing of electrons occurs in high spin complexes, no pairing energy is involved in CFSC. When pairing of d electrons occurs in T2G orbital, to pair up the two electrons in an orbital, an extra energy is required, which is called as pairing energy. For Dn low spin octahedral complex, M is number of pairs of electrons. CFSC general formula minus 0.4 P plus 0.6 Q into del O plus MP. For D5 complex electronic configuration is for high spin T3 2Z EZ2. CFSC 0 del O. Electronic configuration is for low spin T5 2G E0G. CFSC is equal to minus 2.0 del O plus 2P. For D6 complex high spin minus 0.4 del O. For low spin minus 2.4 del O plus 2P. For D7 CFSC high spin minus 0.8 del O. For low spin minus 1.8 del O plus 2P. For D8 complex CFSC is minus 1.2 del O. For D9 complex CFS is minus 0.6 del O. For D10 complex CFS is 0 del O. CFS in tetrahedral complexes. In a tetrahedral complex, the E set has an energy of minus 0.6 del T and T2 set has an energy of plus 0.4 del T relative to barycenter. Electronic configuration for tetrahedral complex EPT2Q. CFSE is equal to minus 0.6 P plus 0.4 Q into del T is equal to minus 0.6 P plus 0.4 Q into 4 upon 9 into del O is equal to minus 0.27 P plus 0.18 Q into del O. Since tetrahedral complexes are high spin and no pairing of d electrons, system for D1 electronic configuration E1 T20, then CFSC is minus 0.6 del T. For D2 configuration is E2 T20 is equal to minus 1.2 del T. D3 CFSC minus 0.8 del T. For D4 minus 0.4 del T. For D5 0 del T. For D6 minus 0.6 del T. For D7 CFSC is minus 1.2 into 1.2 del T. For D8, CFSE 0.48 del T. For D9, minus 0.4 del T. For D10, 0 del T. John-Taylor distortion means John-Taylor effect. John-Taylor effect describes the geometric distortion of nonlinear molecules in certain electronic states, which reduces their symmetry and lowers their energy. This effect is named after the scientists Hermann John and Edward Taylor. This distortion is typically observed among octahedral complexes where the two axial bonds can be shorter or longer than those of the equatorial bonds. Octahedral complexes of D9 and high-spin D4 ion are generally shown as John-Taylor distortion. Two types of distortion is generally observed in octahedral compound: elongation octahedral, compression octahedral. This first structure for elongation octahedral, in this A is greater than E, means to say axial bonds are greater than equatorial bond. This second structure is for distorted structure, means compression octahedral. E is greater than A, means to say equatorial bonds are greater than axial bonds. Example: NiH2O6. All 6 NiO bonds are equal at 2.05 angstrom. No John-Taylor distortion. For CuH2O6 2 positive, 4 equatorial bond at 2 angstrom and 2 axial bond at 2.95 angstrom. This is it absorbs John-Taylor distortion. John-Taylor showed that shapes of transition metal complexes depend upon the filling of d orbital. Let us example of octahedral D9 complex, D9 system, Cu2 system. In this diagram we can see in T2Z, which is lower level, and EZ higher level, in which T2Z is fully filled, and in EZ dz square is filled and dx square minus y square is half filled. There are two ways for electronic arrangements in EZ: when two electrons are in dz square orbital, and when two electrons are in dx square minus y square orbital. When two electrons in dz square, then in this, when dz square are paired, then the z-axis having two electrons, due to more repulsion take place and fall away from metal atom, and X and Y ligands come closer to metal atom. It is called octahedral elongation. But when two electrons are in dx square minus y square orbitals, similarly in when dx square y square minus y square are paired, then the X and Y ligands show more repulsion, due to which Z comes closer to metal atom. It is called octahedral compression. Bond length increase due to repulsion and energy will be increased. This is the John-Taylor distortion in octahedral D9 system diagram. Molecular orbital theory. To explain the characteristics of molecules, like their relative bond strengths, paramagnetic and diamagnetic nature, etc., was developed by Hunt and Mulliken in 1932, known as MOT. When two atomic orbitals combine or overlap, they lose their identity and form new orbitals. The new orbitals thus formed are called molecular orbitals. Molecular orbitals are the energy state of a molecule in which the electrons of the molecule are filled, just as atomic orbitals. Molecular orbital gives the electron probability distribution around a group of nuclei. Only those atomic orbitals can combine to form molecular orbitals which have comparable energies and proper orientation. The number of molecular orbitals formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, they form two new orbitals called bonding molecular orbital and antibonding molecular orbital. The bonding molecular orbital has lower energy and hence greater stability. The antibonding molecular orbital has higher energy and lesser stability. The bonding molecular orbital are represented by sigma, pi, del, etc., whereas antibonding molecular orbitals are represented by sigma star, pi star, and del star, etc. The states of molecular orbital formed depend upon the type of combining atomic orbitals. The filling of molecular orbital takes place according to the same rules as that of atomic orbitals. Molecular orbital theory divides into mainly two types: bonding molecular orbital, anti-bonding molecular orbital. Bonding molecular orbital. The electron present in the bonding molecular orbital result in an attraction between the two atoms. As a result of attraction, the bonding molecular orbital has lower energy and hence greater stability. They are formed when the lobes of the combining orbitals have the same sign. These molecular orbitals are represented by sigma and pi. Molecular orbital theory. The molecular orbital theory is a theory on chemical bonding developed at the beginning of the 20th century by F. Hunt and R. S. Ligand to describe structure and properties of different molecules. The valence bond theory failed to adequately explain how certain molecules contain two or more equivalent bonds, but MOT, molecular orbital theory, explained it in a good way. This is where the molecular orbital theory proved to be more powerful than the VBT. One of the main impacts of molecular orbital theory is that it proved a new way to understand the process of bonding. Valence bond theory: H plus H to H2 atomic orbital. Two atomic orbitals make a molecular orbital. Molecular orbital theory. In this H plus H2 and in atomic orbital 1 bond is present, and in bonding is fulfilled but anti-bonding is half. Postulates of molecular orbital theory. When two atoms come close to each other, their atomic orbital interact with each other to form molecular orbital. As many atomic orbitals participate in the interacting, as many molecular orbitals are formed. The letter SPD is used to represent the atomic orbital. Similarly, sigma, pi, del are used to represent the molecular orbital. Molecular orbital is formed from atomic orbitals of approximately have same energy. Like an atomic orbital, a molecular orbital can also hold at most 2 electrons. Like atomic orbitals, molecular orbitals are associated with 4 quantum number. Types of molecular orbital. Bonding molecular orbital. These are the molecular orbitals whose energy is less than participating atomic orbital. They are more permanent. The electron in an atomic orbital are attached by only one nucleus, while the electron in a molecular orbital are attached by more than one nucleus. Due to increased attraction, electrons start forming bonds. Non-bonding molecular orbital. The energy of these molecular orbitals remaining equal to the molecular orbital participating in the bond. It does not participate in forming bonds, hence it is called non-bonding molecular orbital. When the symmetry of the atomic orbital does not match, the distance between the two orbitals is greater. Anti-bonding molecular orbital. These are those orbitals whose energy is higher than the energy of the orbital participating in bond formation. In this, the system becomes temporary. Energy level diagram for molecular orbital. The extent of overlapping in case of sigma orbital is more than that in pi orbital. Consequently, the energy of sigma 2pz is lower than the energy of bonding pi 2px or pi 2py molecular orbital. Bonding molecular orbital sigma 2s, sigma 2pz, pi 2px, pi 2py. Anti-bonding molecular orbitals sigma star 2s, sigma star 2pz, pi star 2px, pi star 2py. The energy levels of these orbitals have been determined experimentally by spectroscopic methods. The order of increasing energy of molecular orbitals obtained by the combination of 1s, 2s and the 3 2p orbitals of two atoms is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px is equal to pi 2py, pi star 2px is equal to pi star 2py, sigma star 2pz. Energy increases. The new sequence of energy levels from combination of 2s and 2p orbital is shown: sigma 1s, sigma star 1s, sigma 2s, sigma star 2s pi 2px is equal to pi 2py sigma 2pz pi star 2px is equal to pi star 2py is sigma star 2pz. Energy increases. However, experimentally for diatomic molecules have shown figure above sequence of energy levels of molecular orbital theory is not correct for all molecules.